In today's video, we're going to continue looking at the first section of Chapter 2 in our textbook when we're talking about the derivative and the tangent line problem. In our last video, we discussed we looked at finding the slope of a tangent line to a curve at a point. During the last class, there was two main things we focused our lesson on. Our first thing was to figure out how to find the slope of a secant line. And next, we focused on how to find the slope of the tangent line at a given point. So let's review those two concepts right now. So to find the equation for the slope of the secant line, let's look at our graph over here to the right. And when we're asked to find the slope of the secant line, we're asked to find the slope of that black line I just drawn in. So the change in y is my y2, which on my notation in blue is f of x plus delta x, minus my y1, which is in green, which is f of x. So my numerator becomes f of x plus delta x minus f of x over my change in x. And remember how that simplifies down to delta x as we look at my change in my second x value is x plus delta x minus my first x value, which is x, which simplifies down to f of x plus delta x minus f of x over delta x. This is the standard form of finding the slope of a secant line given any 2 points. The second thing we learned last class is we learned how to find the slope of the tangent line at a given point. And all we did to find the slope of the tangent line is we took that secant line equation and we moved 1 point closer and closer and closer to the other point, so close that our delta x approached 0. The change in x approaches 0. So our equation for the slope of the tangent line is the limit as delta x goes to 0 of our f of x plus delta x minus f of x over delta x. These are two essential equations you must learn and must memorize. Also recall that I talked about in class that when you see something called the slope of the tangent line, that is the slope of the equation the instant x is 5 or the instant x is 2 or whatever your x value is. So we also sometimes call the slope of the tangent line our instantaneous rate of change. It's the rate of change at that instant. Our slope of our secant line is the rate of change given 2 points over this interval. So it's sometimes referred to as the average rate of change. So also be able to identify those two definitions and interchange them. Okay, let's review what we learned in the last video, the slope of the tangent line and the slope of the secant line. Today's video, we're going to focus on something called the limit definition of the derivative of a function. And quite frankly, this equation I have highlighted in yellow here is the limit definition of derivative. So a derivative is simply the slope of the tangent line. This equation comes so often, and it was so important that these slopes of tangent lines were so important we gave it its own name. We got tired of writing slope of tangent line, so we just decided to call it the derivative. So the limit definition of derivative is the same as our equation for our slope of our tangent line, as you can see here. Derivative is half of calculus. Most of calculus is either differential calculus or integral calculus. So the concept of derivative is very, very important. So there's a few terminology that you need to know. The word differentiation is the process of finding a derivative. So if I want you to find the derivative of an equation, I might ask you to differentiate the function. The definition of derivative only works if the limit exists. Remember, there are some cases from our last chapter we found that sometimes the limit does not exist. So we can only differentiate a function if that limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x exists. Our notation for our derivative, there's quite a few. And we will interchangeably use all these different notations. So you need to be able to be familiar with all of them. F prime of x is read f prime of x. That means the derivative. A second one, you might see it as dy over dx. This is also read the derivative of y with respect to x. You might also see it as the y variable prime, or d dx of our function f of x. It can also be read, find the derivative of f of x with respect to the x variable, or big D of x of y. Derivative of y with respect to x is how you would read that last one. Derivative of y with respect to x. So these are all notations that mean the exact same thing. That means the derivative. Let's try a few. Use the definition of derivative to find the derivative of f with respect to x. So f prime of x is equal to the limit as delta x goes to 0 of, in my limit formula, f of x plus delta x minus f of x divided by delta x. Substituting in place of every x plus delta x. Now I get 9 minus 1/2 x plus delta x, quantity, minus, in parentheses, 9 minus 1/2 x, divided by delta x. Notice that this time I'm not substituting in a number in place of x. When we do the definition of derivative, we're finding the equation of all the tangent lines to the graph. So we need that variable x. Doing some algebra, we simply just simplify down the numerator, canceling out the 9 and the negative 9, the 1/2 x and the negative 1/2 x, and then the delta x over delta x. So my simplified limit formula is the limit as delta x goes to 0 of negative 1/2. So plug in 0 in place of every delta x, which is just simply negative 1/2. So this tells me that my derivative, or the slope of my tangent line at any point on the line on the line y minus 1/2 x will always be negative 1/2. So let's think about this graphically to help understand what's going on, why I didn't have an x variable in my answer. So the blue line is f of x, 9 minus 1/2 x. If I take the slope of the tangent line at any point on this graph, and it doesn't matter where I'm at, that slope of those tangent lines should always be negative 1/2. So my derivative for this function can always be found by just simply negative 1/2. Let's do a little bit more complex. Let's find the derivative of x cubed plus x squared. So back to my formula, which is our limit definition of derivative. In my function f of x, I'm going to replace every x in that equation with x plus delta x. So I got x plus delta x cubed plus x plus delta x quantity squared minus, and the directions say now find f of x. So that's going to be x cubed minus x squared, or plus x squared, quantity minus, divided by delta x. All that's left to do is do some algebra. So I'll fast forward through this. Make sure you push pause and see how all the algebra works out. We found f of x derivative to equal 3x squared plus 2x. So that means I can use the equation 3x squared plus 2x to find the slope of the tangent line at any point on my function f of x. Algebraic approach to finding derivatives. So now let's explore the graphical approach. Here I have the function x squared. You'll notice I have the slope of this red tangent line is listed here. On my derivative graph, my y value is the slope of that tangent line. So I'm graphing that function. Now as I move my x point on my function graph, notice how it corresponds to my derivative graph. Some key things to notice is as I'm graphing the derivative of a parabola, an x squared graph, notice that my derivative graph is linear. So I'm decreasing the degree by 1. So a x squared graph When I find the derivative of x squared, it becomes a linear graph. So now I have, this time my function value is linear, f of x equals x, and I'm going to trace a few of these points along it. And as I'm tracing my function value, my derivative is constant. It's a horizontal line because the slope of my tangent line is the same regardless of where I'm on this graph. It's always going to be 1 since the slope of that line is 1. So when you have a function that value that is a linear equation, the derivative of a linear function is a constant function or a horizontal line. So let's look at a basic cubic function. So my f of x this time is x cubed. So I'm just going to trace a few points on this graph, and it's going to be plotted onto my second graph, my derivative graph. So I'm using the same x values, but this time on my derivative graph, my y value is the slope of that red tangent line. So when I take the derivative of a cubic function, notice it becomes a parabola, a quadratic equation. I wonder if this is a trend. I wonder if this will continue on if I do x to the 4th, x to the 5th. That's something for you to think about and see if you can figure out, is there a relationship between my function value and my derivative equation. Let's switch to some trig. So here I have f of x is equal to sine of x. I'm going to do the same thing. I'm just going to trace a few x values here, and I'm going to plot the x and the slope on my derivative graph. My function value of sine of x, when I look at the derivative graph, it looks like the derivative is it looks like the cosine of x graph. So maybe the derivative of sine of x is cosine of x. So let's look at if my function value is cosine of x. So here's my cosine of x. I'm going to trace some points on this, and I look at my graph. Now, my derivative graph doesn't look like the sine of x. Instead, I'm going down when I should be going up and up when I should be going down. So that looks more like the negative sine of x, because that's what sine of x looks like. And there's my cosine graph. So derivative of sine is cosine. But here's my cosine graph, basic cosine graph. And the derivative of it looks like negative sine because I've flipped that sine graph across about the x-axis. This time f of x is equal to e to the x. Tracing this tangent line graph, something interesting happens. My derivative graph looks awful lot like my function graph. In fact, we'll find out later through some work that the derivative of e to the x is e to the x. It's one of the few equations whose equation and its derivative is the exact same picture.